Here? Yeah, it's fine.
So we go back to biological applications.
Yeah, sorry for that.
Next talk is by, I'm not sure I can pronounce it, Gwenael?
Gwenael, yes.
Alright.
So first of all, I would like to thank the organizer for inviting me and to speak about how to incorporate biological information in network inference using a structure shrinkage or structure regularization. So in graphical modeling is really important in genomics. The data we usually have come from technologies that measures thousands of biological sequences. So this could be DNA, RNA, protein sequences. And we measure a lot of sequences. So typically the data are high dimensional. So P is much larger than N. And even if you look at a subset of these sequences that are of interest, it's still very large. So here I assume that these measurements are continuous, because I'm going to assume a normal distribution. And the goal is often to infer conditional independent structure, because it gives you an idea about what's going on. You can try to highlight structure and what biological processes are at work. But besides this focus, there's also a lot of side information. Could be genomic annotations, previous studies, or even databases that may be useful to incorporate in your inference. So that's what I'm going to speak about, and I'm going to introduce a model that we developed for network inference and that we have extended to allow the incorporation of such information. Yeah, maybe I should go really quick, but basically we focus on the molecular distribution, and we're interested in inferring the patterns of zeros in the inverse covariance matrix, because these reflect conditional independencies. There's really two general approaches to do that. The first one is the most natural, is to directly estimate the covariance matrix, its inverse, shall I say. And since we are in high dimensional setting, we instead of maximizing the likelihood, we maximize a penalized version of it. But there is also a very popular second approach based on penalized pseudo likelihood, and the idea is just to have to regress everything on everything via a regression model. And it's popular because it's fast. You can parallelize, and you can also incorporate more. Covariate more easily, probably in your things, in your design, and that's so. Here I present a non-Bayesian approach, because for brevity, that the very often the Bayesian approach focuses on the first part, the penalized likelihood estimation, which is most natural, but there's still few works on this, at least to my knowledge, on using pseudo likelihood. For inferring undirected graph. And that's where we have focused, because we thought that there was opportunity there to actually use empirical base to improve inference. So like I say, when you regress everything on everything, you can run things in parallel. But also you might be tempted to actually borrow information across those different regressions. So here's the model that we have proposed. Basically, it uses simple normal gamma prior, and what's important here is that we where's the cursor? Whoops, sorry. Yeah, is that there is a local shrinkage. So the local shrinkage is really the penalization that we make in the neighborhood of each gene. But so it means we penalize the regression coefficient towards zero, but the global shrinkage is provided by the gamma prior on the precisions, and when the parameters A, B are informative, basically since the parameters A and B does not depend on J, then you will tend to borrow information across regression. And yes, so basically that framework that we developed is based on this model, and in short, we use a Bayesian SEM, we use variational approximation to posterior for fast inference with empirical base for the global shrinkage, and we do edge selection via posterior thresholding. and this resulted in this R package. Our interest was in extending that framework. I shall highlight the advantage of already this approach is that usually it has superior stability in terms of when you look at resampled version of your data, and also superior reproducibility when you reconstruct the network. So the global shrinkage really helps in stabilizing your inference. The framework is computationally very fast, at least for a Bayesian approach. Can scale quite well with P, depending of N as well. It's a trade-off. And that's a flexible framework in terms of the covariates you can include, but also in terms of structural regularization. That's what I'm getting at. So basically, the first extension, which was carried out by Gino, a PhD student in Leiden, was to incorporate the prior structure of a network. And how we do that is that we simply specify, instead of having, we specify two types of variances. We simply structure our global shrinkage prior on two variances, on two precisions. The one precision for the edges that are a priori in, and the one that are a priori not there. And we use 2 gamma there instead of 1. So basically it brings more parameters to estimate via empirical base, but that's still fine because you have a lot of regressions. So in the vertical directions, there's still a lot of opportunity, a lot of data to borrow information. In simulation, we could show that that if you vary the quality of the prior network, it really improves quite well the inference. But even if the prior is wrong, it does not make it worse than, it does not harm if your prior information is completely wrong. So here's an example on the P53 pathway in pancreas cancer. We look at, it's a very important pathway in cancer, and it's about 68 genes. And on the top, we just make inference separately for the normal samples and for the cancer samples on the right. And what's different in the bottom is that here we use the prior network on the normal for our inference on the cancer samples. And as we can see that the prior, the edge in red shows the number of edges that are in common between the normal network and the cancer networks. So basically you can see that it tends to encourage that network to have more in common with the other one. But it's not a footprint. There's still a lot of differences. So I think there's still about 50 edges in common between those two here. The extension that we were thinking of is that you can, in principle, generalize that principle and specify any, you can give a different global prior for any partition of your matrix. And basically you have more, the local shrinkage is more flexible because you have more precision parameter to do so. It does bring, although, a lot of more hyperparameter to estimate the empirical base. So there probably one needs to be careful as that each group in the partition needs to probably have cannot have the number of elements within group cannot be too small, otherwise the empirical base will collapse. So that's so the idea was to go beyond these two group structured regularization and to show how you can be more flexible, but it's still work in progress. And I think there's a lot of applications when you want to, let's say, do data integration. Let's say you work on mRNA and microRNA. You want to infer the network, and you have two sets, different sets of covariates. So you basically maybe want to use the data type as a structure, I chose a different type of application, which is quite interesting because there's a lot of different prior knowledge available. So the idea is that we have 164 samples from the cancer genome atlas. So it's protein expression. We have 185 proteins. And basically, we want to use the result of a previous studies, which was done on, it's a pan-cancer study. It means they have look at commonalities between 11 different types of cancer. And the prostate cancer was not one of these cancer. So it's fine to use that prior information. It's independent information. But basically what they did is that they use a bunch of inference methods. They look at selection frequencies, and then they try to carry out, they use different algorithms for detecting communities. So they could cluster group of proteins that seems to work more together. And yeah, so here's basically the result that we would like to incorporate when we make inference in our data. So what I've tried so far, because there's different type of information available, basically, is that you might want to, I was comparing different approaches. The first approach is just to make inference on your data and just don't do structured regularization. You just use one gamma prior that you estimate your empirical base, basically. But the second approach, they define, like I said, they use an algorithm for community detections, and they use different algorithms and they come up with probabilities for that. So basically you can use, so the reddish color is how strong that probability is, and you can, so the second approach that I wanted to look at is to define 6 groups over that, matrix. So you can split your interactions into six groups defined by the membership probabilities. The third approach is to define only 2 groups, one defined by the within cluster elements and the others. And the last approach, approach 4, is to define 7 groups that are defined by the element within each of these clusters, and there are 6 clusters that they have defined. So 6 gamma prior basically, and one for the off elements, the ones that are not within the clusters. So usually and what we could see, so I run the algorithm, and basically what you could see is that, so here we have the sum of a measure of fit, which is given by the marginal likelihood of the SEM. And you can see that when you incorporate prior information, so approach 2, 3, 4, it improves the marginal likelihood. But it seems to do so more for approach 2 when you use membership probabilities. On the prior expectation of the last column of the first table is that we do empirical base. We have different gamma priors. And here I provide the expectation, which gives us an idea about how much you penalize. So if you have just one group, your prior expectation is about 50. And here I have the prior expectation when you have 6 gammas. What's interesting for the approach 2 is that the amount of penalization seems to follow the membership probabilities. Because the first prior expectation corresponds to the group with 0 probability. The second expectation with 0.2, 0.4, and that means as you have a higher probability, you will shrink less, which is quite intuitive. And so I'm still investigating how, what's the effect. So here I was investigating the overlap between the different edge set identified by the different approaches. And you can see that there's not much difference between approach 3 and 4 in terms of fit, but also in terms of selection. They have a lot of common edges. seems there's more difference between approach 2 and the other ones. So basically, we used a Bayesian SEM for network analysis of molecular data, and we have shown how to incorporate prior biological information using structure, shrinkage, and empirical base, and how by splitting the problems into different regressions, you can basically empirical base kick out, and the result that we have suggests that good prior information can really improve a network inference. Although I think there's more work to be done to understand how actually the network structure changes. I've looked at at measure of centrality and what are the most important nodes, let's say, in the network. They seems to be meaningful, but more work needs to be done there. I think flexibility comes also at a price. Even if you're flexible in terms of structure, you still need to think carefully on how to structure your prior and how you would like to carry out structure regularization. Importantly, I just look at a problem with 185 proteins, but I expect that the effect of structure shrinkage will become even more beneficial as P increase, because you basically have more opportunity for empirical base. And I can think of other. I think that in biological data there's always a lot of spare information on the side that you might want to use, and I think there's also interesting application in metabolomic data, for instance, because you know that metabolites are organized into families, and they're usually way more correlated within families than between families. You can think about data integration where you use the data type and that sort of applications. So I'm going to thank you for listening, and I'm going to acknowledge all my co-authors. So it's a work that has been that has started in the Netherlands, that I still continue to work on here. Yeah. Thank you very much. And here are some references.
Can I just ask, so in the what you're setting up is this kind of almost a pseudo likelihood, well, the Bayesian equivalent of the pseudo likelihood, and there they actually need to do some post symmetrization. So I don't remember if you are actually doing some post symmetrization as well, or?
Yeah, we do. So basically, what we do. Is that we do joints, because basically the problem of the symmetry is that you have two parameters for one edge, so we do joint selection of those two parameters for each edge.
It's almost built in the Bayesian step.
Yeah. But there's a way to go around that symmetry problem. I didn't do it originally, but I think there has been a lot of recent work on actually how to just, the way you specify your model, you can just not have this symmetry problem. We just dealt with it differently.
What are your, in your results, do you present the map estimates, or?
No. We don't explore the full model space, basically. So the posterior, so the SEM is just the complete graph. You don't do any selection. You penalize all over the place, but you don't select. The posterior thresholding, actually, the way you do selection is via a simple forward selection, because you can see posterior thresholding as a forward selection procedure. And so there you can define base factor, or try to link the base factor to a Bayesian analog of false discovery rate and all that. Yeah.
What biological validation do you have biological validation for the improvement, or even
Yeah, good point. I think it would be good. I don't have any biological validation. I think it's very hard to actually, I mean, unless I don't have a special collaboration for that, but for the analysis of TCGA data, it's very much use data. I think you need the validation, you need some meaningful, how does it affect, how can you evaluate that your network is actually better? It's very hard. At this stage, I just cannot really say it. It seems to have a better fit. It seems to affect a lot the network structure. I've looked a bit at the structure of the network. There are some biological meaningful interactions. The top interaction seems to be meaningful, but yeah, I need more investigation there. But
Again.